Carboxylic acids, they undergo a lot of reactions. The most important reaction in carboxylic acid is the reaction with a base. I did include the formal charge table in there so that you would know your charges. For example, if oxygen has a bond and the 3 lone pairs, it's a negative charge. And we use this a lot in bases. And if oxygen has 2 bonds and 2 lone pairs, this is a 0 charge. Also, we use it in base. By definition, a base is a compound that has a lone pair, and it can be either strong or it can be weak. If it's a strong, it should have a negative charge. And these are the examples there. These are ionic bonds between the sodium and the hydroxide. Your hydroxide is the base. This is the alkoxide. R can be any carbon chain. It doesn't matter, but the smaller, actually, the faster is the reaction. But anyways, the oxygen, when it has negative charge, this means that it is a strong base, okay? Now, when the oxygen has just lone pairs, so lone pairs are a must condition for the base, because base is the species that has electrons, and it normally uses its electrons to take a hydrogen from the acid. So if it's no charges, then that is going to be neutral. Neutral bases, these are weak bases. This means that the reaction is a little bit slow. The base takes time in order to take the acidic hydrogen. So always, the rule says that the base takes the acidic hydrogen. This means that any hydrogen that you are working with for us for this course, it's going to have a hydrogen in there. So any acid, that we are working in this course needs to have a hydrogen, and the hydrogen is always lost by the base. So the rule says that the base takes the hydrogen of the acid. When the base takes the hydrogen of the acid, it's going to use its lone pairs to make that sigma bond between the base and the hydrogen of the acid. Bases, they change into conjugate acids when they take the hydrogen. Whatever is left from the acid, this is an A-, and that is going to change into a conjugate base. So bases change into conjugate acids, acids change into conjugate bases. Okay? There are different acids in there, but the definition for an acidic hydrogen is a hydrogen that is connected to an electronegative element. Normally, electronegative elements, they take electrons away from the hydrogen and make the hydrogen partial positive. The rule says that the more partial positive the hydrogen is, the more acidic it is, meaning the easiest it is taken by the base. Because, as I said, the base is a species that has electrons. So it can give its electrons to the hydrogen. A partial positive means that the hydrogen needs electrons, and it will take those electrons from the base. So this is why we say the more partial positive, meaning the more electrons the hydrogen need, the more acidic it is. So the faster is the reaction in there where the base comes and takes the acidic hydrogen. Okay? Let's have an example. We have different types of acids, but for this chapter, we are focused on carboxylic acids. But we can have HXs in there like HCl, HBr, and HI. These are the easiest examples. This is the first part of the course 111. So you have your hydrogen in there. So always locate your hydrogen for the acid. So this one is going to be my acidic hydrogen there, okay? And that acidic hydrogen, of course, is connected to chlorine, and the chlorine is electronegative, so this hydrogen is partial positive because the chlorine is pulling electrons from the hydrogen, making it in desperate need of electrons. So that hydrogen now will take electrons from where? From the base. Now, the basic part of the molecule is the part where it has lone pairs. So this is why it's important to write your Lewis structure for these types of reactions so you know where your lone pairs are. So here my oxygen in there. So that is going to be a base Now notice that water is a neutral, so it's going to be a weak base. You are responsible to know the type of base that you are working with, whether it's a strong or weak. Strong if the base is negative, weak if the base is a neutral. Okay? And then you apply the rule. The base from the oxygen, from the oxygen. So the oxygen uses its lone pairs and take the hydrogen of the acid. So what I'm going to end up having here is my conjugate acid, because always the base turns into a conjugate acid. That was my base. It took a hydrogen from the acid. Guys, you can go to the table up there and see that if oxygen has 3 bonds, it needs to have a lone pair and a positive charge. So I have a lone pair, and it makes sense because I used one lone pair to make a bond with the hydrogen. The other one stays the same. Please put your charges. This is positive charge. That is going to be my conjugate acid. Plus the leftover is the Cl minus in there. And you don't have to put the lone pairs, but I am putting the lone pairs, and that is going to be the conjugate base. The chlorine already has 3 lone pairs. And when you break this bond, the electrons also add. So this is why the chlorine has 4 lone pairs in there. Again, acids turn into conjugate bases, and bases turn into conjugate acids. You always start the reaction by the base taking the acidic hydrogen. When your acid is a carboxylic acid, it's the same thing. Base is going to come and take the acidic hydrogen. The difference here is that this base is going to be a strong one, so the reaction is going to be faster. So that base here, so that is going to be the base. The sodium is just a counter ion that balances the charge of the base. So that is going to be a base, and it is a strong base because the oxygen has a negative charge. So again, you highlight your base. Here you go. From the oxygen. Where is your lone pair? It's on the oxygen. So you're going to use one of the lone pairs of the oxygen to make a bond with the hydrogen of the acid, because the base takes the acidic hydrogen. So this is going to be my reaction here. You do have an acidic hydrogen, so that hydrogen is going to be my acidic hydrogen. Bases take acidic hydrogen, so you're going to make water, right? The OH, when it connects with the hydrogen, you're going to make water. So bases turn into conjugate acids. So the OH of the base is going to turn into water. That is conjugate acid. Plus whatever is left from the acid is this part over here. Just go ahead and write it down. And you do have an oxygen. When oxygen has one bond, we're going to refer back to the table. When oxygen has one bond, it will have 3 lone pairs and a negative charge. Please write it down. So you're going to see 3 lone pairs in there and a negative charge. Of course, negative charges do not exist like this, because for every negative charge there is a positive counter ion to balance it. And the positive counter ion here that you have is sodium. Okay, and that is going to be my conjugate base. You guys, always the rule, whenever you write any reaction, the reactant side need to be balanced with the product side, meaning charges. I'm talking here about the charges. So if you have a positive negative, then you need to end up having a positive negative in the product. The charges should balance on the reactant side and on the product side. So here, what did I make? Is basically the base. We call this the base of the acid. The base of the acid is nothing but the acid when it lost its hydrogen. So if you have this acid in there, which is a propanoic acid, let's write the name of this acid. So propanoic acid. So when propanoic acid loses its hydrogen, then it becomes we call it a carboxylic acid salt. Why we call it salt? We call it salt because of the charges that it has, because of the negative and positive charges. This is salt. It comes from an acid in there. So I have to name it as such. I have to name it as a salt. So if I want to name the carboxylic acid salt, these are the rules that I would need to follow. So to name a salt, the first thing that we do, we name it the cation that we are working with, and the cation here is sodium. Okay, we leave a space, and then we name the acid it is derived from. So this salt is derived from propanoic acid. We drop the ic acid, we add an ATE, so it's going to be propanoate. Okay, this is not an ester. I know esters, they add an ATE at the end, but this is not an ester. Why it's not an ester? Because it starts with an ion, with a positive ion. So this is how you know that this is a carboxylic acid salt and it is not an ester. Let's have an example, another example. Again, I do have an acid, so always start with the acid and label your acidic hydrogen. And then go with the base, go to the base and label the basic part in there and know what type of base you are working with. So this one is a strong base because the base has a negative charge. This is why it's strong. And then apply the rule that the base takes the acidic hydrogen. So I'm going to group the hydrogen to the OH and make water in there. So that is going to be water. So I know that my base changes into a conjugate acid. Plus, now my conjugate base is going to be the leftover of whatever I have left from the acid. I know that my acid is benzoic acid. You are responsible for all of these names, okay? So that is benzoic acid in there. Whatever is left is that minus the hydrogen. So you take the hydrogen out. So this is the oxygen in there. That oxygen is a negative charge. Look at the table in there. You should have 3 lone pairs. You don't have to show your lone pairs. Just the negative charge is fine. And then please balance it with any counter ion you have in the solution. You have potassium, so go ahead and add potassium in there. And that is going to be my conjugate base, which is my carboxylic acid salt. Now let's go ahead and name it. We name it from the benzoic acid. So you need to know the name of the acid that it came from before you name it. So always put the cation first, which is in this case potassium. It came from benzoic acid, drop the ic acid and add an ATE, so it's going to be benzoate. Okay, so always whenever you're working with an acid-base reaction, label your acid, label your base, allow the base to take the acidic hydrogen and make the carboxylic acid salt. Now this reaction is pH dependent, not temperature, it's a pH dependent in there. And because I am forming a base, I need to increase the pH of the solution. Okay, so we call this a reversible reaction because it depends on the pH of the solution, if the pH is high or pH is low. So let's say, for example, if I have this and I say, okay, at high pH, what I'm going to get? High pH means basic. Low pH means acidic. Okay. So at high pH, the base is going to react with the acidic hydrogen as usual in there. And I'm going to favor the formation of my base because high pH is for formation of the base. Okay, so here I do have my base, which is water. It's a weak base. So the water is going to come, same as the reaction above. The water is going to come and take that acidic hydrogen. You're going to form a positive charge in there. That is going to be a conjugate acid plus my conjugate base in this case, which is the propanoate. So that is going to be my propanoate, and then I'm not going to write the lone pair. So that is going to be the propanoate, and that is going to be the propanoate. Okay, ion. We call it an ion in there. If you want to be specific, then this is called hydronium. Hydronium ion. You don't have to name that in there, but this is the positive charge that balances the negative charge, and we call this an ion in there. You don't have to name that plus part or positive part unless it is a potassium or sodium. Then go ahead and name it. If it is a hydronium, it's fine. You can skip that. So the idea here is that at high pH, the reaction is going to favor the formation of the propanoate ion, which is what? Which is a conjugate base. Okay, that is at high pH. If my reaction goes at low pH, this means that it is reversible. Then this is at low pH in there. So if I start with these two as reactants, then my product is going to favor the formation of the acid at low pH. So always remember, high pH, I am forming the base. Low pH, I am forming the acid, because acids exist in a low pH medium and bases exist in a high pH medium. If you look at the pH scale, you guys, you do have 7, which is a neutral, and then you can go less than a 0, but for us, I mean, we can start with a 0 in here. The pH scale is up to 14, so more than 7, this is going to be called high pH in there, and that is going to be basic. And less than 7, that is going to be low pH, and that is going to be acidic. So always monitor the pH of the solution. Here it's saying at high pH. So high pH meaning that I am favoring to form the base in there. So water here is going to come take that acidic hydrogen and form the H3O plus. So that is going to be my H3O plus in there. And that is going to be my conjugate acid, because we said that bases always they change into conjugate acids. Plus, now the leftover of the acid, once the base takes the hydrogen, now this is the base. Okay, so that is going to be the base, and at a high pH, the base is always favored as a product. So if I want to name this, that is going to be a benzoate ion. Okay, because there is no potassium or sodium next to it, but it is still balanced with the hydronium ion. So I can still name it hydronium benzoate, but still, I mean, you don't have to name the H3O plus, so just leave it aside and name this as a just an ion in there. Okay, now if I go ahead and reverse this, so if I want to reverse it at low temperature, then I would need to show you that I am using the benzoate and the H3O plus as a reactant. And I'm going to ask you what is the product that will be at a low pH, not a low pH. So you guys, always you look at the product and see what you are forming. And this is how you know what is your pH median. So if you're forming the base, then this means that you are working at a high pH. If you're forming the acid, then this means that you are working at a low pH. Now, another reaction of acids is with alcohols, and this is called esterification. Esterification is the process to make esters. Normally, esters are fragrances. This is one of your labs is to make an ester, and normally we make an ester starting from an acid and we react it with an alcohol. This is one way of making an ester. The reaction goes in presence of an acid, and the acid here, H plus, is any acid. Like for example here, I gave you like sulfuric acid. Without it, the reaction does not happen. So this is why that H plus is a must, because it speeds up the reaction. Okay, and this reaction is pretty much very straightforward. The acid normally loses its OH, and the alcohol loses its hydrogen, not the OH. Alcohols, they don't lose an OH and you have R's like that. No. Alcohols, for these reactions, they lose just a hydrogen. Acid lose an OH, so I'm gonna form water to be my byproduct. And then the remaining parts, I am going to just put them together. So the oxygen there, I'm just going to bond it with the carbon of the carbonyl. So my product here is going to be an R, C double bond O. Okay, I'm going to make a bond. Let's go ahead and draw this bond in a different color because this bond here is broken, right? So I'm going to make a new bond. So this is going to be the new bond, and you add the rest of the ester, which is the O, and then the R prime in there. Notice that you are making the connection between the C and the O, the oxygen of the alcohol here. So you are reacting an alcohol with a carboxylic acid, and your product here is going to be an ester. Okay, now again, the ester has two parts here. It has two parts. One part over here which comes from the alcohol, and the other part, this one comes from the carboxylic acid. Okay, plus of course your byproduct that you are making here, which is water. So this is going to be, you can write it as H2O, or you can write it as an HOH, whatever you prefer, but this is going to be my byproduct in there. My main organic product is the ester. And as we said, esters are fragrances, meaning that we can create different combinations of fragrances and also flavors, by the way, by simply changing the type of the alcohol and the carboxylic acid that we are reacting it together. We can form an ester that has a banana fragrance, a strawberry fragrance, a pineapple fragrance, depending on the alcohol and the acid that you are working with. And that is going to be one of your labs. Okay, so let's have an example there. The moment you see an acid being reacted with an alcohol, always the alcohol is going to lose a hydrogen and the acid is going to lose an OH. You form the ester bond, you combine together. I always start with the leftover from the acid first. So I do have a 3-carbon chain, and then I have my carbonyl. Here you go. Then I am making a new bond. That is my ester bond. This is going to be the new bond that will be connected to the oxygen, and then the CH2, and then the CH3. So I have my my oxygen in there, and then my CH2 and my CH3 here. So that part comes from the alcohol. That part over here comes from the acid, plus of course my water. Guys, please pay attention for the presence of the H plus in there. This is a reversible reaction. This is why we use that reversible arrow in here. This means that we can go from the reactants to the products and from the products to the reactants. But H plus is a must for this reaction to happen fast. Okay. There are other catalysts that we use in this reaction other than H plus in there. It depends on the actual reaction. But for us, we're going to keep using H plus. Let's have another example here. The alcohol loses the hydrogen, and the acid will lose the OH, and then you're going to combine everything together. So I'm going to start with my leftover from the acid. I am making that a new bond, ester bond, and then that ester bond will be connected to the oxygen of the ester. And then whatever I have next to the oxygen, I just copy it. So I do have 2 CH2s in there. It's up to you if you want to go ahead and write them as condensed or as skeletal. I'm just going to keep the skeletal over here. So I have a carbon, I have another carbon, And then I do have my isopropyl in there. Just make sure that you copy every single carbon and you don't miss any. Okay. Now, another way I can ask this question is I can give you the ester, and I can ask you, go ahead and make this ester. So to make this ester, we know that the ester needs to have an alcohol part and a carboxylic acid part. And we know that the easiest bond to break is the ester bond. So you always target the ester bond to break it. And this one over here, we know that this one comes from the alcohol. So all what you need to do is add a hydrogen to it, okay? Because we know that the alcohol loses a hydrogen. So we're going to add a hydrogen to it. And then the other part, we know that it comes from an acid. So this whole thing comes from an acid. So this one comes from a carboxylic acid. So all what you need to do again is go ahead and add an OH to it. Copy it exactly as you see it. So I have a carbon, 2, 3, 4, 5, and then I have my carbonyl. So simply add an OH in there. Okay, and here you go. I got my acid and I got my alcohol. You react those two together and you form the ester.